Now the problem with this setup is that I don't see anybody. So I only see what you see. So if you have any question, I will stop from time to time just to make sure that you're still there. So give me some sound from time to time. At least I know I'm not talking to myself. Okay.
Should I turn on the camera?
Yes, that would be nice.
Okay, okay. I'll turn on my camera.
Okay, very good. Thank you. If you could turn on the camera, it would be great. Okay, super. So let's see. Okay, so the topic of this presentation is about coloring graphs. And everything started with the problem of coloring a map, a geographic map, where the question was to graph the region of the map, so not in such a way that not two adjacent regions have the same color. So for example, if I try to, I can put the red here. Let me just change the brush. I can put red here, then I cannot put it there, I can put it here, and I can put it there, but now I cannot use the color red anymore. So I try another color, and I put a blue here, for example, and a blue here, and then I need another color, and I put the green here. Now, if one wants to be able to answer this general question, which is find the smallest number of colors that you need for any map, there is no way you can continue like this. So what people have done, they associated a graph with the map. And the way to do that, then they put a vertex in every region, like this. And then they connected two vertices. Let me just put the vertices even here. 3, 4, 5, and 6. And then they connected those vertices accordingly to whether the regions are adjacent or not. So for example, those two regions are adjacent, so you connected those two vertices. Maybe I should be thinner. And then you connected those two vertices, and then this, and this is also connected, and this is also connected, and then this is connected with this, and this, and this, and this. So what you end up with is a graph. So let's go here. Let's reproduce this graph. And now you can see that with a map, you can associate a graph. So this is a map. This is called the dual graph of the map. And now you can rephrase the coloring problem as coloring the vertices of the graph in such a way that no two adjacent vertices have the same color. So it's the equivalent question. And of course, you can also go back from a graph to a map if adjacency of the regions is the only thing that you care about. So you can go back from a graph to the map if only adjacency of region matters. Okay, so the problem of coloring a map is equivalent of coloring a dual graph of a map, so that coloring the vertices, so that no two adjacent vertices have the same color. So now the question is, which graphs are dual of planar graphs? Because it's not the case that an arbitrary graph can be associated with a map. And here the answer is very simple. The answer is graphs which can be drawn, on the plane with no crossing, with no, when I say crossing, I mean edge crossing. Okay, so if you have such graphs, which are called planar graphs, every planar graph corresponds to a map, and every map gives rise to a planar graph. And now we have an equivalent question, which is a question in graph theory, that is, what is the smallest number of colors needed to proper color the vertices of a planar graph so that no two adjacent vertices are the same color. So this is how the problem has been investigated. And of course, so all of you know what the answer is. What is the answer? This is the
I can't
famous,
really remember. I think it's 4, right?
Very good. This is the famous 4-color problem. So very good. So this number is called the chromatic number. The smallest number is called the chromatic number. Chromatic number of the plane, and the answer is 4, and was proved in 1976. Okay. Now, so this is a theorem that has been proved. Now, by introducing the non-crossing requirement, one added a geometric component to the problem. So at the beginning, graphs have no geometry involved, but as is the moment that you are requiring that there is no edge crossing, you are adding a topological requirement. And that implies that it makes sense to ask questions. What would happen if you draw a graph on a different space? So the plane is just one type of surface. What about if we change where we are drawing the graph? And the first thing, of course, would be, what about drawing on a sphere? If you draw a graph on the sphere with no edges crossing, then would this smallest number, same formulation of the problem, just the space has changed. And it turns out that if you are dealing with the sphere or the plane, is the same problem. So one can draw, so this is a result that is a graph can be drawn with no crossing, on the plane. On a plane, if and only if it can be drawn with no crossing on a sphere. So by drawing it on a sphere, you are not changing the problem. It's the same problem. So the question is, what about other surfaces? And for example, what about if you have a torus, like a donut? This is a torus. And then you might have a two-holed torus. There's another type of surface. This is two-holed torus. And what about if you have a 3 and so forth? So those are different type of surfaces. And the sphere is denoted by S sub 0. The torus is denoted by S sub 1, which is the number of holes that you have. This will be S sub 2, and this will be S sub 3, and so forth. And those numbers are called the genus of the surface. So in general, when you look at S sub p, this positive integer p or non-negative integer is the genus of the surface. And you can think of the number of holes that the donut has. And now I think it's clear that if you draw a graph on a torus, you can draw it in this little region here. So the chromatic number of a torus should be larger than the chromatic number of the plane, because if you can draw something on the plane with no crossing, you can draw it in a small region in the torus, and that is flat. And in fact, this problem was investigated soon after the four-color conjecture was stated at the end of the 1800s. And for the torus, the chromatic number was actually proved to be 7, much before the chromatic number of the plane was proved. In fact, if this is the general definitions, so just to formalize what I said, now the question is, what is the smallest number of colors needed to proper color the vertices of the graph, which can be embedded in S sub P in the same requirement, so that not two adjacent vertices in the same color. And throughout the years, in this investigation was completed by the same time the Four Color Theorem was proved, and there is this general formula. This is a formula for every genus. In fact, it works also when P is 0, as you can see, because when P is 0, you get 4. And when P is 1, you get 7, but this formula works for every P. Okay, so this is just to show you that a simple problem that started as a curiosity, like coloring a map, developed into this mathematical subject of coloring graphs on surfaces. Now let's go back to Earth, meaning sphere of the plane, and let's look at a new problem. That is, if you have a graph, let's try to find a function whose value at every positive integer gives you the number of proper coloring of a graph. Okay, so you want to count how many different proper coloring a graph has by using at most lambda colors. So here is a lambda missing because I cannot use. Okay. So this is a counting problem, and we want to find this function, and this function is what is the title of this presentation. So let's look at two extreme cases where this answer is very simple. The first family of graphs for which this answer can be found very quickly are the complete graphs. Complete graphs are graphs where every vertex in the graph is connected to all the other vertices in the graph. Okay, so when you have so let's see, so this is so lambda is the number of colors. If you only have one vertex, how many possible colorings do you have? Tell me. If I have 3 colors, how many possible ways can I color one vertex?
3 points?
Well, only one vertex have 3 different ways. Agree? If I have 3 colors, I have 3 different ways of coloring one vertex. And if I have lambda colors, I have the function is just lambda. That is the number of colors. Very good. What about if I have the k sub 2, which is 2 vertices, 1 edge? So, and again, I have lambda colors available. How many different ways can I color these 2 vertices so that adjacent vertices are assigned different colors?
Lambda times lambda minus 1.
Very good. Lambda times lambda minus 1. What about if we have 3 vertices?
3, then it's lambda times lambda minus 1 times lambda minus 2.
Okay, very good. So it seems clear what happens. So when you have a k sub n, you will have k times, lambda times lambda minus 1 up to lambda minus n plus 1.
Yeah.
So it's very easy to find the number of columns for complete graphs. Then we go to the other extreme. Then we have isolated vertices. So these are graphs, I should say, isolated vertices. Which means no edges. Now, if I have only one vertex, how many different ways can I color this vertex?
Still lambda?
still lambda. What if we have two vertices by
It's
no edges?
lambda square.
Lambda square.
Yeah.
And then you solve what
Cubic. Yeah.
Lambda to the fourth, and then there will be lambda to the other.
Yeah.
It turns out that those two simple family of graphs are enough to find the number of coloring for any graph by doing this procedure. This is called the fundamental equation. So let's explain each one of them. And the first thing to observe is that this equation relates the number of colorings, not it doesn't mean, it's meaningless to say one graph is equal to another graph, right? So we say that the number of colorings on the graph on the left equals to the number of colorings on the graph on the right. So this equation again is with respect to the number of colorings. So what is this equation that is extremely important? Where you look at the graph and you look at two vertices which are not connected by an edge. For example, you look at this vertex here and this vertex here. And then there are two cases. Now you need to assign colors to those two vertices. And there are two cases to consider. One case is that those two vertices have the same color. If those two vertices have the same color, then it's the same as combining or identifying those two vertices together. So imagine that you are taking this, so this is the graph. You have this. Now imagine that you take this vertex and you move it on top of this vertex because they have the same color. And if you do that, the graph that you obtain is this graph, which one edge less than the previous graph. And this graph corresponds to the case when those two vertices have the same color, the one that I encircled with red. But you can also have when those two vertices have different colors. And if you have different colors, you may as well add an edge between those two vertices because this edge will force the graph to have different colors. So the number of colorings of the graph on the left equals to the sum of the colorings of the graphs on the right. So in here you are identifying a vertex, define a vertex, and here you are adding an edge. Add an edge.
Yeah.
Now this equation can also, since it's an equation dealing with the numbers, can be rewritten in the form B. And this doesn't make sense, so I want this. This.
Oh.
Okay. So now I can use this procedure either following the equation. Yes. You tell me. Is it okay?
Yeah.
Very
Okay,
good.
okay.
So I can apply this formula or this correspondence between colorings either by following the procedure in A or B. And it makes a difference as we are going to show. So let's say I start with this graph. And now I apply property A by considering those two vertices, this one and this one. Then what do I get? Well, you can try to do it as I do it here. So I want to identify those two vertices in one graph and draw an edge on the other graph. So the adding of the edge is simple. And when I identify the edge, what happens? Well, this vertex gets identified with us. So I'm going to have this and this still, this and this. But now when I take this vertex and identify with this, you realize this goes away.
Yeah.
And now if I continue, so this is plus, if I continue applying this property A to the remaining graphs, slowly, step by step, you end up with this. So the number of colorings of the graph on the left equals the number of colorings of this linear combination of complete graphs. This is the whole point. Those are complete graphs. Complete. And I know what the formula for complete graphs is. This was
excuse
lambda.
me?
Yes.
Sorry, the first one, do we need to connect the two on the left upper side and right upper side? Like the complete one? So for the
Yes, must be a complete one. Thank you. Yes.
okay.
Thanks. Thank you. And now we know this is lambda minus 1 up to lambda minus 4. Plus 4 times lambda minus 1 times lambda minus 3 plus 3 times lambda minus 1 lambda minus 2. And if we multiply all of this together, which is a nicer way to do it, we end up with the polynomial. Now you realize why they're called chromatic polynomial, because those functions are actually polynomials.
Yeah.
Now, if we apply the equation in the form B, the fundamental equation B, let's apply it to a smaller or simpler graph, otherwise the computation goes. And this, so this will be what? Will be, remember what the, so, I will have this. And then minus this. And now you can see in here the number of edges decreases, does not increase. So if you repeat this process here, we end up with the number of colorings of this graph on the left is a linear combination of the number of colorings of isolated vertices, and we know what the formula is, and this is again a polynomial. So you can see that by applying this procedure to an arbitrary graph, we always end up with a polynomial, and we can already predict two fundamental properties, at least this one. Actually, maybe not necessarily, we need some work, but let's see what the properties are. So this is what is fascinating about this polynomial. So you are doing the polynomial that counts the number of colorings, and now you try to ask yourself, do the coefficients of the polynomial have any meaning with respect to the graph? The first observation is that the sign of the coefficients alternates. And moreover, that none of them is 0. Okay, so you cannot have a lambda cube and then going down to lambda to the first power. The first coefficient, Isabel minus 1, is the number of edges of the graph, always. The second coefficient will be the number of edges of the graph chooses 2. So the number of pairs of edges minus the number of triangles of G. And actually there is a formula for every coefficient in terms of the structure of the graph. So those coefficients have a lot of information about the graph, which is very surprising. And then we have a little bit more, I guess, sophisticated properties which I will just, this is called the unimodal property, that they don't seem as important, but actually are very important. If you study combinatorics, you want to study properties of sequences, and there's a very important property, which means that those coefficients will increase, and then we reach a peak, and then we'll start decreasing. This is the property that is captured by this. And now let's verify what we just, these properties from the, in the picture that, for the graph that we considered before. So we had this graph, and the number of colorings we said was equal to lambda to the fifth minus 6 lambda to the fourth plus 14 lambda cubed minus 15 lambda squared plus 6 lambda.
Yeah.
So we can see that the sign is alternating. 6 is the number of edges of the graph. And what about this coefficient? What should that be? Well, that should be 6 chooses 2. So this coefficient should be 6 is the number of edges chooses 2 minus the number of triangles. Well, let's see. I have 6 edges. So it's 6 minus 6 chooses 2 is what? Is 15. Right, 6 chooses 2 is 15, minus 1 is 14. Matches. And again, let's just verify those. There are others. We can also verify this one, for example. This increasing property that I was mentioning above. As you can see, 1 is less than or equal than 6, less than or equal than 14, less than or equal than 15, and then it goes down. So this is the unimodal property. Actually, those are, okay, very good. So now I don't know how much time I spent talking, but I could stop for much more, but well, let me just mention something else, and then maybe I will not cover everything. So the question is, this polynomial gives you information of the graph only when you are evaluating at positive integers, because it gives you the number of colorings. If you are evaluating this polynomial at 1/2, you have no idea what that means you as far as the graph. But the question is, what about negative integers? For example, what about -1 or -2 or -3? And the funny thing is that even for the negative integers, there is a meaning associated with it. And let's just focus on lambda is equal to -1. And we need to introduce another concept, which is a cyclic orientation of a graph. So what an orientation of a graph is, just you have edges and you decide a direction. This is an orientation. This is what orientation means. And now you want to assign a direction to the vertices so that you never end up with a oriented cycle. Okay, because this will be a cycle. Okay, so how many, let's see, how many acyclic orientation do you think a square has? You take a look at it, but try to figure it out, and try to see how tricky the problem is, and then we'll do it together. Try to count them, the number of possible ways of assigning direction to the edges, so that you don't have a cycle by following the directions.
So every edge has two orientations. So it should be like the n's, right? N square of 2. I mean, 2 n's, something like.
Well, it would be 2 to the 4 would be 16, right? That's a very good
yeah.
idea. Very good idea. So let's find the total number of ways of orienting the edges, and then which is 2 to the 4th.
Yeah, 2 to the 4th.
And then we take away the possible orientation which gives you a cycle. But there is only one way, there are only 2 ways to give you a cycle, right? You can either...
Oh, yeah. To -2.
Very good. Or you can have the other direction. So very good. That's actually easy to do it. So that should be 14. And the theorem that one has is that that number can be obtained by evaluating the chromatic polynomial at -1. So if you are evaluating the lambda, or you're assigning to lambda the value -1, the value of the chromatic polynomial in absolute value is the number of acyclic orientation. So let's look for the square. Let's verify. Again, these are not proofs, but I don't think it would be appropriate to do a proof. This is what we found before.
Yeah.
And now let's evaluate it. This is what I've been calling FG of lambda. And let's take the absolute value of this polynomial evaluated at -1. In here, there is no need of taking absolute value, but in general, there is. This is 1 plus 4 plus 6 plus 3, and this is 14. Now, you realize that if the graph is extremely complicated, the counting of a cyclic orientation is going to be very, very difficult to do. This was a very trivial example that you find a very nice way of solving it. But in general, there are no such tricks. And this is a much nicer way. And it shows you, again, another surprise in the meaning of the chromatic polynomial with respect to the structure of the graph. Okay, maybe I want to finish this short presentation just by mentioning two unsolved problems in the topic. So if you like this topic, you can actually do some work towards this in solving those 2 questions. So let's look at the first question. If you have a graph, then you have a polynomial. That is the chromatic polynomial. But the question is, if someone gives you a polynomial like this one, lambda to the 4th minus 3 lambda cube plus 3 lambda square, this polynomial satisfies the properties that we listed before as far as the properties of the coefficients. But the question is this polynomial the chromatic polynomial of the graph or not? So the general question is, if someone gives you a polynomial, can you say whether that polynomial is the chromatic polynomial of some graph or not? It's a very difficult question. Nobody knows the answer. What people have done, they consider special cases, and they answer this question for special cases. So this is why I say this is a nice question that students can work on, because you can take some special subcases and try to answer that question for smaller or for some conditions on the polynomial. By the way, the answer here is no. Another open question is related to finding the graphs that maximize the number of colorings. And the reason why this question is important is because graph colorings are important in computer science, because the complexity of algorithms can be compared to the number of colorings of certain graphs. So if one wants to know how many operations needed to perform some sort of algorithms, that will be answered by finding the number of colorings of a graph. This is why this will give you an upper bound. And again, why did I put maximize? Because for minimize, the question is very simple and people have already answered it. but for maximize is actually a difficult question. There are results when the number of vertices is very large. This is the number of vertices. I should put lambda here, not 10. But for not large n, n being the number of vertices and the number of edges, if the number of vertices and edges is not large, then it's very difficult to characterize the graphs. Okay. So the last comment that different graphs can have the same chromatic polynomials. So for example, those graphs have the same chromatic polynomials, and those graphs, for example, have the same chromatic polynomials. So it's not an invariant, it doesn't allow you to go back in general. And that led to my next example, but I think I'm going to skip it. If you're curious about this topic, we can meet again in Queensland and
Okay.
do some coloring together.